Today we're going to talk about a laboratory method called titration. The way that we're going to perform this titration laboratory procedure in class is to take an unknown concentration of an acid. In our specific case, we're going to use hydrochloric acid. So it's an unknown molarity concentration of acid. We're going to put that in a flask, and we're going to add an indicator to that flask. We've done a lab with indicators. In this particular titration, the indicator that's going to work very well for us is phenolphthalein. So we're going to put some phenolphthalein into that flask as well. And then we're going to take a known concentration of base. Now, that's not a very good drawing, but I'm going to keep it anyway. We've got something called a burette. The burette has a lever on the side that we're going to be able to control that will add a known concentration of a base. In our case, we're going to use sodium hydroxide. So known molarity of a base, in this case, again, NaOH. And we're going to add that drop by drop to our flask. And we're going to keep adding that base to the flask until we reach what's called an equivalence point. And it's going to be signaled by a color change. Our phenolphthalein is clear when it's in an acidic solution, but as soon as that flask, the solution inside that flask turns just a tiny bit pink, we're going to know that it's reached an equivalence point, a neutralization point, if you will. And we're going to be able to use the information of exactly how much of our base that we add to our unknown solution, and using some mathematical calculations, be able to determine what the concentration of our acid is. So let's say that we did a similar titration. This time we're using 10 milliliters of an unknown concentration of sulfuric acid. We need to know that that's H2SO4. And we titrate it in our burette with 1.5 molar NaOH, and it takes 22.5 milliliters of that base to reach the end point, to reach that color change, so we know that we've got an equivalent amount of acid and base in that solution. It's asking us then to find the molarity of that acid. So the first thing that we need is to come up with a balanced chemical equation. I'm going to erase a little bit of this because I'm going to need this room in just a moment. And we're reacting H2SO4 with NaOH. And when that reacts, we've done this before. We did this in the previous assignment. It's going to take 2 sodium hydroxides to balance 1 sulfuric acid, because our our hydroxides and our hydrogens must match up. And we're going to need to know the information here in just a little bit, that for every understood 1 mole of H2SO4, there are 2 moles of NaOH. And as soon as we know that, we know we produce 2 moles of water, or 2 water molecules. And the salt in this case, remember, metal first, is going to be Na2SO4. So there's our balanced chemical equation, and now we're going to label it. There's a couple of rules that we want to, actually 3 rules that we want to keep in mind. The first rule is how we label. The first rule is that we want to label all volume values, we'll just say all volumes, as liters, and all molarity values as moles per liter. It's going to be very important, just trust me, in making these much easier calculations if you'll just do that. So when I have this 10 milliliters of H2SO4, I'm going to label that as 0.0100 liters. Remember the rule of 3. And to get from milliliters to liters, we're going to move the decimal 3 places to the left. So I've got 0.0100 liters of H2SO4. The next value we need to label is that we have 1.5 molar NaOH. So 1.5, remember the rule, moles per liter. Please record the correct units. It'll make it so much easier in a moment. The last value to label is 22.5 milliliters of our base. So rule of 3 again, 0.0225 liters of the NaOH. And finally, that we're looking for the molarity, the moles per liter for H2SO4. So those are the values we need to have labeled. And now it's time to start our problem like we always do. Now, there's a lot of numbers here that we have to work with. So that's what the next 2 rules are for. The second rule says that, or my second rule says that we are never supposed to start a problem with a value that pertains to the unknown. So to shorten that a little bit, never start a problem with an unknowns, not really great grammar, but we'll use it anyway, unknowns value. Because of that, we are not going to start with 0.0100 liters because it is a value that pertains to the unknown. The third rule is that we always start the problem with the simplest unit, not a complex unit. We never start a problem with a conversion factor. We want the simplest unit to start the problem. So looking at the values we have for NaOH, our known, we have liters and we have moles per liter. We don't want to start with a conversion factor, so we're not going to start with 1.5 moles per liter. We're going to start with the 0.0225 liters of NaOH. So we've used that value. And now we may not know what comes next in the next conversion factor, but we should know that it's got to be liters of NaOH. And the thing I love about solution stoichiometry problems, which is what this really is, a solution stoichiometry problem, is that generally all the values you need are given to you in the problem. There are no molar masses to look up. It just makes it a lot easier when the values are right there in front of you. And the only other value we have that pertains to our NaOH is this 1.5 moles per liter. So keep in mind how we want that to be put into the conversion factor. We need liters on the bottom, so it's an understood 1 liter on the bottom and a 1.5 moles of NaOH on top. So that cancels the liters. We're left with 1.5 moles of NaOH. Now, the next thing we need to do, we're out of values for NaOH, and we don't want to find information about NaOH in the first place. We want information about sulfuric acid. So now it's time for our change the substance to conversion factor, and remember that's our mole ratio. We've already established that we need these values up here, our coefficients, to come up with that mole ratio. We need moles of NaOH on the bottom in order to cancel. So it looks like we're going to need the 2 moles of NaOH on bottom and the 1 mole of H2SO4 on top. That's going to cancel out moles of NaOH. And finally, guys, this is where you're going to mess up if you're not careful. Because look at what our units are supposed to be. Our units that we want are moles per liter for our unknown. We're so used to having that last unit cancel not really used to coming up with a complex unit for our answer. So keep in mind, we want liters on the bottom, and the only value we have left that has liters in it is that 0.0100 liters. So we're going to put that on bottom. And I'm emphasizing this because I want you to see that we're dealing with moles per liter here. Do we want any other units on top? And the answer to that is no. We want just simply a 1 up there on top. So that's a little bit different from the conversion factors we've seen before, but that's what we have to do in order to end up with moles per liter in the end. So with that in mind, do this calculation. 0.0225 times 1.5 divided by 2 divided by 0.0100, and to 2 sig figs, which we need because of our 1.5 right here, we end up with 1.7 moles per liter. Now, when you come back down here and you're ready to report this value officially, now we want to take it back to 1.7 molar H2SO4. So there's our value, our answer for that particular problem. Now let's go on to the next one then. This one's just a little bit different. Notice that this one is asking you to solve for milliliters instead of molarity, so it's going to be set up a little bit differently. We still need a balanced chemical equation. We're reacting aluminum hydroxide with HNO3. So let's get that balanced chemical equation first. Aluminum hydroxide plus HNO3. Notice that we've got 3 hydroxides, only 1 hydrogen, which is going to tell us that we need a 3 in front of here to balance it. And that's going to tell us that we need 3 waters over here, 3 water molecules. And our salt, metal first, is going to be aluminum, just 1 of those. And if you'll notice, there are 3 nitrates on the other side, which is going to give us our 3 nitrates in our salt. Just a little bit of a shortcut. You can remember that aluminum is a +3 and nitrate's a -1 and come up with the same answer. But like I said, it's just a little bit of a shortcut on coming up with the salt formula. So there's our balanced equation. We're going to label again. 0.750 moles per liter for our aluminum hydroxide. It's asking us to find that in milliliters. Now, all my values that I'm recording and writing down here for labeling are going to be in liters. So that's a big clue on my part that my units at the end may need to be converted. So when I'm taking a test, you don't have to put a smiley face on your paper, but I put a lot of smiley faces on mine when I know there's something that I might miss. So I'm going to put a smiley face on milliliters so I hopefully won't forget to convert that in the end. So I've got my aluminum hydroxide labeled. Now for my nitric acid, 0.0350 liters. Remember, we want that recorded in liters, and 1.20 moles per liter for the concentration of the nitric acid. So stop it real quick and just see if you can figure out what value here you need to start the problem with based on our rules above. Hopefully you came up with the fact that you can't start with the 0.750 moles per liter for 2 reasons. It's a complex unit and it's part of the unknown. So it comes down to a choice between liters and moles per liter, and we're always going to choose the simplest unit. So our starting point here is going to be 0.0350 liters of HNO3. So we've used up that value. And the only other value up there that pertains to nitric acid is the 1.20 moles per liter. Remember, we want the understood 1 liter of HNO3 on the bottom and the 1.20 moles of HNO3 on top. We should have made that red for the way I want to do this. And now we need our mole ratio. Remind yourself that you're going with the mole ratio for an understood 1 ALOH3 for every 3 HNO3s. We want HNO3 on the bottom, so 3 moles of HNO3. So we'll cancel moles of HNO3 for every 1 mole of ALOH3. So far we've canceled liters of HNO3, we've canceled moles of HNO3, we have moles of ALOH3 left. Be very careful. It's very tempting, and I see it happen a lot of times, for people to flip this last conversion. We've used up everything except the 0.750 moles per liter. Think about what needs to go on bottom. Since we need moles of ALOH3 on bottom, we need the 0.750 on bottom and the understood 1 liter on top. So watch out for that. That's going to cancel moles of aluminum hydroxide and leave us with liters. When you plug this in your calculator, 0.0350 times 1.20 divided by 3 divided by 0.750, we end up with 0.0186666, etc., until your calculator runs out 7. And it's tempting to round this to our 3 sig figs this time and record the value, because indeed it's going to be 18.7 to the correct number of sig figs liters of HNO3, or excuse me, of ALOH3. But remember, little smiley face up above says we need this in milliliters. So be sure you go back the other way. And I just wrote that right. I actually converted it before I got to the end. Again, this is what I meant to write. 0.0187 liters is what we're tempted to write, but reminding ourselves with our smiley face that we want that to be in milliliters. That's how we come up with 18.7 milliliters of ALOH3. And even though I kind of messed that up at the end, I think you get the idea about the confusion that you can get into if you don't bother to make some kind of notation about what kind of units you want at the end for your answer. So watch those things. AP is really bad about asking for units that you don't come up with in the answer and you have to convert, so be careful for that.